أول شيء حابب أتأكد تسمعوني كويس.
نعم، أسمعك
طيب
بوضوح.
أول شيء السلام عليكم جميعا. حاب أشكر أول شيء القائمين على هذا المؤتمر والمنظمين جميعا. الله يعطيكم العافية كلكم، وسعيد جدا لرؤية مثل هذه الجهود بعالمنا العربي، وأتمنى إن شاء الله أنها تكون بداية انطلاقة كما ذكرت دكتور أحمد في البداية لمؤتمرات علمية جادة في عالمنا العربي. فشكرا لكم، وشكرا مرة ثانية لإتاحة الفرصة لتقديم بحثي مع نخبة من العلماء والباحثين العرب. فأول شيء حاب أعرف من نفسي، يزيد الوهيبي، طالب دكتوراه بالفوتونيك أند كوانتم انفورميشن جروب at إمبيريال كوليج لندن. وراح أتكلم اليوم عن جزء من رسالة الدكتوراه، وهو بعنوان Detection Lobe Hole Free Bell Test over Long Distances، أو بالعربي اختبار بيل آه، بدون ثغرة الرصد عبر المسافات الطويلة. طيب، راح أبدأ بmotivation, then I'll present our protocols, performance compared to other protocols, and then I will conclude. أول حاجة الهدف بسيط جدا، وهو to distribute genuine non-local quantum correlations over the longest possible distance. The keyword here is genuine quantum correlations, and by that we mean these correlations need to pass a lobe hole free Bell test. And so, what's a lobe hole? What's a Bell test, and what's a lobe hole free? What are the lobe holes? Okay. So, first, a Bell test is basically an experiment which checks whether distant systems behave according to local classical physics or display the non-local correlations predicted by quantum mechanics. For example, if we have an entangled photon source and which emits like two photons that are entangled, and we send one photon to distant parties labeled Alice and Bob, then Alice and Bob will perform local measurements on these particles, and they will choose their measurement settings randomly and independently, labeled here by X and Y in this figure. And then from the measurement outcomes they get here labeled A and B, they will do the experiment again and again, and from these measurement outcomes they will get the probability distributions for the or the joint probability distributions for the different outcomes A and B. From these joint probability distributions they compute a number, basically, which is the Bell parameter is. For local theories this number has to be less than 2. A violation of this means these correlations cannot be obtained by classical means. Now, what are the lobe holes? There are basically three main lobe holes. First, the locality lobe hole, which means the two parties that are performing the measurements need to be separated by space-like separation, which means they need to perform the measurements faster than the time light would take to propagate from one lab to the other, or from one party to the other. The second is the freedom of choice lobe hole. As we said before, like they need to choose these measurement settings X and Y randomly and independently. The last one, and it's the most difficult for long distance, is the detection lobe hole. They require high detection efficiency. Now, since the goal is to distribute entanglement over long distances, then the locality lobe hole can be closed directly because they are separated with long distances. And then the freedom of choice lobe hole can be closed by using true random number generators, for example, quantum random number generations. And then we are left with the detection lobe hole, which is the hardest, especially over long distance. So what is the detection lobe hole? So assume we have the entangled photon source in the ideal case where two particles are emitted or two photons, and there are no loss in the channels. Then we expect two detections in the detectors that are in the paths of these photons, because the channels are lossless. So each detector will register a photon. Now, in reality, because the channels are actually lossy, there are all these different possibilities. So we have the ideal possibility of the two photons arriving. We have the possibilities of one photon being lost and the other will arrive. And then we have the possibility of the two photons being lost. Now, if you want to do a Bell test and calculate the S parameter, you have you can do different strategies in the realistic scenario. For example, what you can do is just consider the case where the two photons arrived and both select them by measuring the coincidences in the two detectors, and then just ignore the other possibilities. This is called the fair. If you want to do this, then you need to assume that what you detected actually are fair sample or fair representation for all the events that were emitted by the source. And hence, this is called the fair sampling assumption. And if you do this, you could achieve a Bell violation regardless of your detection efficiency. But this opens the detection loophole, which means this violation could be obtained by classical means. You cannot, if even if you get a violation, that does not mean the resources were actually quantum. It could be obtained by carefully designed classical source also. So what we are aiming for is a loophole-free Bell test where we do not want to make these assumptions. For this, you need to have high detection efficiency. So there is a minimum threshold for the efficiency that you need for the detection. And that depends on the states that you are using. So, for example, if you're using maximally entangled state and you want to pass the CHSH inequality, you need the detection efficiency above 82.6%. If you're using the Eberhard approach where you can optimize the state and use non-maximally entangled state, then you can tolerate more loss and you only need the detection efficiency of 66.7%. Now, let's look at the back and what experiment has been done in this area. So, 10 years ago, in 2015, there was a major development in this area. Three independent groups demonstrated for the first time loophole-free Bell tests. Two of them were done in the photonic platform using polarization entanglement. One was done with a hybrid system of entanglement between spin and photons. And later in 2023, a more recent experiment was done using superconducting circuits. If we look at all these experiments, the longest distance was 1.3 kilometer for the experiment with the hybrid entanglement between the spin and the photons. And this is because they use what's called event-ready scheme, as we will show later. But even this distance is not that large. So we want to even go larger. So we want to scale up to do like quantum networks and quantum communication. We want tens of kilometers and hundreds of kilometers. So a long distance closure remains open, mainly due to channel loss. It's really hard. And why do we want to achieve this? Basically, there are fundamental and technological reasons. For the fundamental reasons, as I said, a loophole-free Bell test of a long distance has not been done before. And then we want to explore the non-locality test with different photon mode entanglement. As Dr. Baha mentioned in the beginning, you could you could encode your photons in the path instead of polarization or other degrees of freedom. And we want to explore this as it's the most promising approach to do this, as we will see later. We want to understand the limit the limit of for how long we can maintain these quantum correlations without breaking. And there are, of course, technological reasons like device-independent quantum key distribution. You need a loophole-free Bell test to get a secure key that is device-independent. And also we want to explore distributed quantum sensing and scalable quantum networks. So basically, it's very clear that the photonic approach is naturally the most suitable for long distance Bell test. How this can be done? There are different ways you could do. You could have one source in the middle at a station called Charlie, and then you send one photon to Alice and the other to Bob. And this approach, although it is simple and it has a lot of complexity, but it has many limitations. It's highly sensitive to loss, since the losses in the channels will also be will contribute to the loss budget that you need to close the detection efficiency loophole at Alice and Bob. So, for example, if Alice and Bob and the sources, like the overall efficiency is like 85%, and you want to pass a CHS inequality, then you need you can only afford 3% more because you need a total of 82%. And if you want the Eberhard inequality, then you can only afford to lose 17% more. And that means if you are only considering the loss of the channels themselves, not the losses of the detectors, then you can only travel between half a kilometer to 4 kilometers at most. Another disadvantage of this scheme is if you're using SPDC sources, then there is no heralding, and these sources are actually probabilistic, and you do not really know which events were successful when generating the entanglement. A more or a better scheme that you could use is what's called the inventory, the entanglement distribution. So in this scheme, Alice and Bob have the entanglement sources in their labs. So they use their own entanglement source, which produce two entangled photons. They send one mode to a middle station, Charlie, and keep one for their labs. Charlie performs what's called a Bell state measurement and announces the outcome. Upon a successful measurement at Charlie, then the remaining modes at Alice and Bob will become entangled. This is what's called this is basically entanglement swapping. Now you could do this in different ways. You could do it based on two photon interference, where you need two photons to arrive, one from Alice and one from Bob. This, although is better than the direct transmission, but it still scales linearly with the distance because you need two photons to arrive at the station. While you could do it with just single photon interference at Charlie, and this means you need one photon to arrive at Charlie, whether it's from Alice or from Bob. The key thing is that you need not to know from which path it came. Is it from Alice or from Bob? And that's the challenging part about this. And this is the famous like twin field scaling. And it scales, the advantage of this scheme is it scales as square root of the channel transmittance. And it will lower the detection efficiency. But the challenging part about this scheme, it requires phase locking. So there are a lot of work on this scheme. People have proposed and demonstrated experimentally this scheme, well, not in a Bell test, but for entanglement swapping. And for this, they use, you could use different sources at Alice and Bob. The most common approaches in the literature is Alice and Bob both use two-mode squeezed vacuums, and then, or Alice and Bob both use single photon entanglement states. Then, upon a successful measurement at Charlie, Alice and Bob will share the single photon path entangled state. Will share this state. Now, the thing about this state is it cannot reach the Abraham limit, and you still require an overall detection efficiency above 82.6% to achieve a lobe hole free Bell test, which is challenging. So what we propose is using a hybrid scheme, like where Alice uses a two-mode squeezed vacuum, but Bob uses a single photon path entangled state, and then we herald the vacuum and two photon superposition entangled state, the 00 plus 1 1, and we herald it in a way that is tunable. We can tune the amplitudes of these components, and that will allow us to reach the Abraham limit, or make the requirement list to close the detection efficiency lobe hole. And these efficiencies can be easily obtained using today's detectors and sources. And so this is the realization for our protocol. We propose using two-mode squeeze vacuum at Alice and Bob, but Alice will send one mode directly to Charlie, while Bob will herald one photon and use the other to pass through a beam splitter and create the single photon path entangled state. And then upon a single photon detection at Charlie, Alice and Bob will share the entangled state 00 plus 1 1. This will be the heralded state, and as I mentioned, you can tune this state by controlling the experimental parameters like the transmittivity of Bob's beam splitter. This is the ideal heralded state. The actual state is a mixed. The actual heralded state is a mixed state. But the nice thing is that by tuning the experimental parameter, we can suppress the noise term that's coming from the interaction with the environment. So, for example, by using a very low transmittivity at Bob, we can suppress this term and purify our state, or like have our ideal entangled state. And also, there is the advantage of scaling as square root of 2. It has the twin field scaling. Okay, so this is just to show the entanglement tunability of the shared state. As I mentioned before, you could achieve maximally entangled state if you satisfy this criteria, or you could tune it to other amplitudes given the losses that you have in your channels, because each loss has a specific weight for the amplitude to achieve the maximum violation. This is just to show the success rate probability for our protocol compared to the other protocols. Although our protocol is lower than that protocol where they use two-mode squeezed vacuum, but the advantage is in this second result, where The green figure, the green line, sorry, curve is our protocol, while the gray one is for the previous protocols. So as we can see, above two or above this red line, we can achieve a lobe hole free bill violation, and the x-axis is the detection efficiencies that you need. For all previous protocols, you need above 82% to achieve a violation. While for us, we can reach the fundamental limit, what's called the Abraham limit of 66.7%. There are different ways you could achieve the Abraham limit using polarization entanglement, but this also has the linear scaling with the transmittance of the channel and has a much lower violation, as we can see in this figure. And these are experimental results that has been demonstrated using polarization entanglement, these marks. Okay, so what are the applications for our protocol? As I mentioned
يزيد.
before, we could use it for quantum key distribution, device-independent quantum key distribution, and also random number certification of truly random numbers. The dashed lines here are from previous protocols, while our protocol is the solid lines. And recently, there is this paper which used our protocol to calculate the maximum key rate you can obtain using our protocol compared to the previous protocols. A and B, B is our protocol with, and the dash is, A is the previous protocols. So basically, this shows that, and the dash is when you are using photon number resolving detectors, and without dash is when you are using just click detectors. So we can see that our protocol can provide positive secret key rate even at lower detection efficiencies below 90%, which was very challenging to previous protocols, and that's why this experiment has not been done so far. And if you are able to use photon number resolving detector, then not only our protocol is more loss robust, but it also almost have the same key rate at higher detection efficiencies as the previous protocols.
يزيد،
Now, the remaining question
محتاجين
is why the single
نشرح.
photon path entangled state cannot reach the limit, while our state, the 00 plus 1 can. And mainly the reason is because of the superposition with vacuum. You see the single photon path entangled state has one photon. There is the possibility of one photon in each component, in each amplitude, and then the loss will affect both amplitudes, so you cannot actually mitigate the loss. While for our state, because vacuum, you cannot attenuate vacuum. Vacuum is loss robust. So by tuning the loss will only affect the one term, and by tuning the C1, you can minimize the effect of the loss, and you can make your state more loss robust. In future, we are looking to utilize this scheme for quantum relays or quantum repeaters and multipartite entangled distribution like GHZ states and non-locality recyclings and quantum networks. Thank you for listening, and I'll be happy to answer any of your questions.
شكرا جزيلا يا يزيد. يعني يعني استمتعنا بمحاضرتك. شكرا جزيلا للشرح الوافي. للأسف الوقت ضيق لاستقبال الأسئلة، فلا أعلم إن كان هناك سؤال فيما يخص محاضرتك. يعني هناك وقت لسؤال واحد. أم، طيب، هناك سؤال عن ال Quantum Key Distribution. لا أعلم إن كان له تعلق شديد بعملك اليوم. تسمعني يا يزيد؟
ايش السؤال؟
Quantum Key Distribution.
اي well هذا المين ابلكيشن لهذا الورك. Well, this work has many applications, but the main application is device independent quantum key distribution. So to do quantum key distribution, there are like you could do it with the ultimate goal of quantum cryptography is what is called device independent protocols. You want to distribute keys that are secure regardless of the way you implement the experiment, regardless of the devices that you use in your experiment, just by doing the experiment, you guarantee the security of the key that you generate. And you can only achieve that if you generate, if you distribute or use genuine entanglement, like lobe hole free entanglement. Then you can achieve this ultimate security. Other than that, there are always assumptions. You need to assume that the device is protected, the device is not, like there are many side channel attacks that you need to take into consideration.
تمام، مفهوم. أنا شاكر ليك مرة أخرى، وسعداء بوجودك معنا.
العفو، شكرا
وشكرا
لكم.
لك، وننتقل بإذن الله للمحاضر التالي. دكتور عمرو، معنا هنا؟
أيوة معاك. أهلا وسهلا.
نعم، أهلا